Good afternoon, everybody, and thank you for joining us this afternoon. We have now opened up the virtual lobby. I now see that everybody is transitioning into the virtual auditorium. So please bear with us just one moment to ensure that we have captured all of our attendees, and we will begin momentarily. Okay, good afternoon once again. Thank you very much, everybody, for joining us. It is my great pleasure to introduce you to Beverly McKeon from Caltech.
Good afternoon, everyone. Thank you, Jen, and thank you for trekking over to this session. It's a great pleasure for me to be speaking in this SIAM meeting. Obviously, I'd much rather be that we're all in a position where I could speak to you in person, but kudos to SIAM for keeping science moving forward. My name is Beverly McKeon. I'm a faculty member. I'm the von Karman Professor of Aeronautics in the Graduate Aerospace Laboratories at Caltech. Today I want to talk to you about some work we've been doing, really applying some old ideas from hydrodynamic stability to turbulent flows. And so I describe the title here as Structure and Scale Interactions in Wall Turbulence, and I've called it a modal puzzle. I'll tell you what I mean by that as we go forward. As ever, these pieces of work are large collaborative efforts, and so I'd like to acknowledge the contributions here of Arti Sharma, Ryan McMullen, Kevin Rosenberg, Rashad Moarif, Daniel Chung, Ian Jacobi, and Subramaniam Davuri, who have all at various times worked with me at Caltech and are now liberally distributed around the world. The work that I'll show you has been supported by the US Air Force Office of Scientific Research and through the Office of Naval Research. Nope, we're not moving. Why are we not moving? There we go. So the context of what I'm going to show you is sort of summarized here, and I wanted to frame it this way because it's a great pleasure to see that Nick Trefethen is the recipient of the 2020 John von Neumann Prize and is lecturing in this conference as such. So what's underpinning the results and the analysis that I'll show you is really this difference between the eigenspectrum and the pseudospectrum. So on this slide, just given a toy problem, two operators S and P, and the top one, S, is a normal operator. The bottom one is going to admit non-normal growth or transient growth. It's a non-normal operator. So what we're showing here are the eigenvalues. Let me see if I can use my mouse. Hopefully you can see the eigenvalues here at the red crosses. And these concentric circles for the normal case are what happens to the spectrum if you perturb the operator. So this is the definition of the pseudospectrum down here. So we have perturbation to the operator. So this is for a general operator A, perturbation of size epsilon. And if you have a normal operator, the pseudospectrum, or the location where the eigenvalues move, will be concentric circles based around the eigenvalues. And if we look at the value of that perturbation, or we're going to call this the resolvent norm later. So we take the value along this dotted line and we look at it here. This is some measure now of how amplified, we're going to interpret this as amplification of an input signal. Let's look now at this second operator here, P, non-normal. It has the same eigenvalues, the red crosses, but now the pseudospectra are not concentric circles anymore. And so if we look again on this dashed line here, the real part of the eigenvalue 0, we can see first of all that the peak response, or the peak amplification, the peak movement of the eigenvalues corresponds not directly to where those eigenvalues were in terms of the imaginary part of lambda, and also that it's much larger. Okay, so in this case it's larger than 1. Over here it was less than 1. And so this paper by Trefethen et al. Really laid out the importance of these phenomena for fluid flow, and especially for transition. I'm going to talk to you about how we've thought about these ideas in turbulent flow. So here's the outline. The modal puzzle of the title is shown here. So how do we exploit what we can get from linear dynamics of the turbulent Navier-Stokes equations that govern fluid flow to model a full nonlinear representation, nonlinear characteristics of wall turbulence. So I'm going to step through these things in our brief time together. There's quite a bit here. I'm going to try not to go too far into the detail of the equations, but to give you the broad brushstrokes picture of what we're doing and why this might be important. So I'll give you a brief introduction to turbulence and some history of the linearized or linear analyses for turbulent flow, and then talk about what we call the resolvent formulation or resolvent analysis, and how that is, at least on paper, a complete representation of the nonlinear system of equations. I'll show you that the spatio-temporal structure that analysis of the resolvent gives us, and how that can lead us to a sparse reconstruction of turbulent flow data. I'm going to show you that the formulation admits geometric self-similarity at the level of the response modes of the resolvent and at the level of turbulent structure. And I'll go through what I mean by these as we go forward. I'll briefly show you that just as in the classical literature, there's an asymptotic representation of the eigenmodes there. We also are able to get a semi-analytical modal representation. And I'll close with some more information about the nonlinear piece of the puzzle. So how do we exploit the linear dynamics to represent what's going on in the full nonlinear system? So I should have said at the beginning that I'm coming from the aerospace engineering world, and particularly fluid dynamics. And so there's a lot of structure here, there's a lot of interest in turbulence. I'm going to give you just a brief overview of some of the things that we know about wall turbulence. But the goal here is both an enhanced understanding of the physics behind how turbulence self-sustains, what that means for computation and prediction for engineering type flows, and also as a hope for control. So how does physical insight give us the intuition to imagine methods for control? So imagine, if you will, flow over a flat plate indicated by this orange arrow. So there's a black flat plate. And if we were to measure the well, in this case, the temporal mean, so if we were to time average the streamwise velocity above the wall, we would get this kind of a curve here, which would be blunter, so a higher gradient closer to the wall than an equivalent laminar flow because of the mixing inherent in turbulent flow. And this mean hides a wealth of information and complexity, so an instantaneous snapshot of the edge of the boundary layer here is shown from this laser-induced fluorescent image from Gadel-Hack et al. So there's a lot going on, bulginess, intermittency, definitely structure on different scales. And if we step through some of the history of understanding of turbulent flow and interrogation, this is a classic set of images from Klein et al. Showing how if you release lines of hydrogen bubbles, you can see them best on this top image here, parallel to the wall. If they are in the free stream and they don't intersect with any turbulent activity, then they will just convect downstream as parallel lines. But whenever they start to intersect with these bulges, you can see the complexity associated with the mixing of those bubbles into the boundary layer. And if we move down closer to the wall, you can see some distinct patterns here. So there are some streaky patterns. So down very, very close to the wall, those bubbles get drawn into long streamwise aligned streaks. And there's an element of that in the middle one, but sort of a lot going on in that middle plane. So this boundary layer really is telling us how a flow adjusts in this frame of reference from a free stream flow out here down to a no slip, no penetration condition associated with a rigid wall for a viscous flow here. So velocity is a free stream value out here and 0 down close to the wall. But in between, there's all this structure. If we look in a streamwise wall normal plane, and now this is a particle image velocimetry image from my laboratory, nothing special about this one particularly. Here we are able to image the trajectories of particles and use those to back out the local velocity in this streamwise wall normal plane. And you see the signature now of rotation in this sense. The colors here are the magnitude of the velocity vectors relative to the mean. If we use the same technique in a wool normal plane now, and we highlight the activity that is a fluctuation slower than the mean velocity, you see the imprint of these very long structures. Okay? And if you look very closely, you'll see that on either side of these are red and blue dots, and those are the vorticity into and out of the plane. So, or rather, if I were here in person, I would be waving my hands and moving around. But if the streaks are aligned in this direction, there's vorticity rotation up and out and back down either side of these streaks. And if we go to a simulation from Wu and Moyne from Stanford Center for Turbulence Research, we can see where some of that structure, that vortical structure is coming from and how we're seeing some of it. So this more complicated figure here is variously described as a forest of vortices, or really just a complex accumulation of vortex structures. You can see they're color-coded by distance from the wall. You can see that there's a lot going on, but there is structure here. And this is a robust kind of structure, meaning that it repeats on very many different scales. And so really the origin of this work was to try to understand how the robustness of these structures is reflected in the equations of motion. Now, everything I've shown you here was observed either in a laboratory scale facility, nothing particularly special about the scale of any of these things. The simulation, the direct numerical simulation on the right here was state of the art. So that certainly involves a lot of computational power. This one is now, I think, about more than 5 years old. But obviously that's not the type of scenario that we're interested in as engineers as a rule. And so the things that we are interested in at the large scale are shown up here in the top right. So flow next to a wall has obvious implications for things like transcontinental natural gas pipelines, aviation, commercial aviation, and shipping. And those are in a different flow regime. So in the laboratory, our Reynolds number, so a non-dimensional number given by some measure of velocity, a velocity scale, some length scale divided by the kinematic viscosity. In the laboratory, that's about 10 to the 5. By the time you're up in these large scale industrial or engineering applications, you're up in the order of around 10 to the 8. And you could take that even further if you wanted to look at the atmospheric surface layer. To give you some sense for why this is such a difficult problem, if we took this tanker and we took one that again was sort of state of the art, the largest in the global fleet a few years ago, and we stood it on its end, it would be about the height of the Empire State Building in New York. On that hull, by the time you reach the end of the hull, these long streamwise aligned coherent structures here, or these long streaks that I've shown you in that wall parallel plane, they would be the height or the equivalent length of the height of a 2-story building. And to give you some measure of the scale separation, by the time you're trying to resolve the smallest scale, the viscous scale there is some fraction of the size of a human hair. The boundary layer would be about as tall as me if I reached up as high as I could. So there's a vast range of scales here. Complete fidelity simulation of all scales is out of reach and will remain out of reach for decades, even with the most optimistic view of the increase in computing power. So understanding how to reduce the complexity, reduce the cost of modeling, and really supply a suite of tools of different fidelity is something that many people are working on. So our particular approach, as I mentioned, is to think about linear dynamics. So I'm going to specialize here first, as I have mentioned, to flow close to a wall. So the very specific branch of turbulence that we refer to as wall turbulence. That's an important distinction because there's an inhomogeneity imposed by the presence of the wall. We recognize that as being a mean shear in the wall normal direction. I'll also specialize for now to incompressible flow, Newtonian fluid. We're going to look at flow between two flat plates, so psi flow, channel flow, duct flow. All of those things can be relaxed, and actually this technique is increasingly being used for turbulent flows of all sorts of geometries. But we'll start with the simplest case. And these equations would be familiar to you if you had looked at the stability problem. So under what conditions are you unable to write down a laminar solution, or sustain a laminar solution? For our purposes here, we're going to define now a mean. So I'm going to do this for the velocity field, three-dimensional, and the pressure. We're going to define a temporal mean. We'll specialize to a spatio-temporal mean later on. But for now, this is a function of the three spatial coordinates for u and p, and then a fluctuation on top of that, denoted by the small, the lowercase. And if we substitute these into our Navier-Stokes equations that govern fluid flow, we get these two equations for the fluctuation. So this is just a statement of continuity. And over here, this is the momentum equation formulation where I've put the nonlinear term, quadratic, for these conditions on the right-hand side. I've marked it in red because that's clearly nonlinear in the fluctuation. But then for a turbulent flow, this capital U, this mean, is also impacted by the presence of the nonlinearity. So this capital U is not a solution of these equations in the absence of any forcing, or if you're familiar with fluid mechanics, in the absence of the Reynolds stresses. So left-hand side now is linear in this fluctuation U. The right-hand side is clearly explicitly nonlinear. That is not a new formulation. Clearly, if we were in the laminar regime and we were looking for an equilibrium solution, we would set the right-hand side to 0, and we would be looking at, potentially looking at an eigenvalue analysis. Malkus in 1970 postulated that this turbulent mean here, U, was the solution of these equations that made them neutrally stable in this turbulent case. That turns out to be not true for wall turbulent flows, but it is true for some other categories of flow. But for what we're looking at here, these turbulent mean flows close to a wall are stable. They're linearly stable. All the eigenvalues are in the lower half plane. So since that work, there's been a large body of work that's exploited this particular formulation here. And you can do that in two ways. So you could, if you have a right-hand side, it's just called D here, we can either think about an initial value problem. So what kind of input disturbances on the right exhibit the largest transient growth? And so we know that from the work of Trevethan that even if all the eigenvalues are stable, you can still have a large energetic growth before ultimate decay. So that's what we call transient growth. And so this work goes back to Butler and Farrell and several authors going back a long way. I haven't given the full list here. The other way to think about this is the continuous problem. So Farrell and Ioannou considered what happened if you had a continuous forcing of exogenous source or origin. So what kind of forcing do you have to put in on the right-hand side to get out a field, a fluctuation field that looks consistent with the types of things that I showed you in the outline of the structures in turbulent flow. A really important paper in this area was written by Jovanovic and Bamier in 2005. They considered a laminar flow, but the viewpoint that they introduced was that of an input-output problem. So again, what kind of input do you put in to get an output on the other side that has specific characteristics? And so the work that we put forward in 2010, very closely similar to Wang and Kosu, also in 2010, considered this for a turbulent case. The difference between these two pieces of work is that we're going to retain the meaning of D as being the nonlinear piece up here. And to do that, we need to retain that full form of the equations. Wang and Kosu used what's called an eddy viscosity to model the impact of the nonlinear term. And there's been lots of subsequent work. This is also from Jovanovic's group, Zer et al., again, trying to shape the right-hand side. So this is the picture that we're going to talk about for the rest of today. So we have some linear dynamics, that's the left-hand side of these equations. And we're going to have the right-hand side be explicitly that nonlinear term exciting the linear dynamics. So thus far, just rearrangement of the equations. So here's the picture. I'll remind us that this does require the turbulent mean profile as an input. So I'll come back to that towards the end, but let's assume that we can either measure that reasonably well. It's not necessarily that too difficult to get that in experiment or perhaps from a RAND simulation or some other means. So this was the generic picture. This is the picture that we're going to work with. And for the channel flow, we're going to Fourier transform in the homogeneous directions. And in the channel flow, that's the streamwise direction X, spanwise direction Z, and because this is a stationary flow in the statistical sense, the temporal domain as well. I'll use this shorthand here. So we can do that on both the output and the input side. And you'll recognize this as an oblique wave modal type representation. And C here will have some importance then as the wave speed in the streamwise direction. So we can, for each bold K, that's this triplet in the exponential here, we can write this formulation. So U sub K is equal to H at K times F of K, or acting on F of K. Now the F, as we've said, is not this nonlinear interaction term, so that is a function of this larger UK or U at K prime. So the full formulation is given here. We haven't solved what's known as the closure problem of turbulence, we've just reformulated it. And I've put in a green box this transfer function now between F and U, the resolvent operator. And in our 2010 paper, we expressed this in terms of singular modes. So we did the singular value decomposition, Schmidt decomposition to singular value decomposition. So here, the left singular vectors are the response modes. The right ones are the input modes, or we'll call them the forcing modes. And the sigmas are the singular values, or the gain. So all of this analysis here is setting up to find the basis which has the largest amplification within this framework here at each wave number. So let's go back to the picture that we opened with. So this is now a concatenation of those two images. So the concentric circles for the normal operator, which was S, and the these are oval pseudospectral lines for the non-normal operator. And so our interpretation now is that we have some linear dynamics, and that operator has a spectrum, and it is perturbed by this nonlinear term. And if we're interested in this particular formulation where we have non-amplified, non-decaying waves, so the neutrally stable case, we're interested in the perturbations that push the eigenvalues up to the axis, to the zero axis here. And we're especially interested in the ones that do that with a very large gain, so the ones that move those eigenvalues the most. And so the interpretation now of this SVD is that we seek inputs or perturbations to the operator, which are described by the basis phi, that give us a response psi scaled by these singular values. To give you some sense for the moving away from the toy problem, what we see in the real case, we can specify which bold K we look at. In some cases, the sigma 1, which is equivalent to the norm here, norm of H. In some cases, sigma 1 can be less than 1, so this can be a forcing that is not amplified. In some cases, this magnitude can be something like 10 to the 5, 10 to the 6. So you can have an immense amplification of a small disturbance if it is the most dangerous disturbance to that system. So let's take this a little further. So here's this representation. The green box is to point out that we're in the linear world. So back here on this picture, green was linear, red was dealing with the nonlinear piece. So here's that SVD. Again, we're going to do that at each bold K. And let's take a look at what those singular values look like for a specific set of wavelengths. Now I've moved out of wave number into the wavelength domain for a particular Reynolds number and a particular wave speed. So this is J is going down the SVD, and sigma J here, even the peak sigma J is less than 1. So this is one of those instances where even if you put in a large forcing, you will see a smaller response on the output. For the channel flow, these come in pairs, just symmetric, anti-symmetric pairs. But you can see that there's at least, or close to an order of magnitude roll-off here. So this is one of the instances, in the interest of full disclosure, this is one of the cases where the roll-off between the first pair and the second pair is actually not that small relative to some of the things that we see, but I didn't want to cherry pick the things that we showed. So this roll-off can be really steep, really rapid, giving an approximation of this, or we can expect an approximation of this resolvent operator in a low rank way. So we can look into that, whether that's a good approximation to make. So really what we're talking about is if we want to reconstruct H, do we need infinity up here, or can we truncate? And we can look at that by looking at the resolvent norm relative to the sum of the singular values. Here, the interpretation is if we took all of these phi j's at a given k, and we excited all of them with the unit amplitude forcing, what would we see for the weighted size coming out the other side? So sigma times psi. So this is a measure, if you like, of energy associated with the first pair of singular modes if all modes were excited the same way. Now, of course, that's not true in a real flow, but if this roll-off is steep enough, it might not matter in terms of capturing a good basis to represent the turbulent flow. So what you see on the right is at this same height that we were looking at on the left, this quantity plotted versus streamwise wavelength and spanwise wavelength. And where this is red, clearly this is a large value. So in the red locations, almost all of the response of the operator is captured in sigma 1 by sigma 1 and sigma 2 in the first two modes. And therefore the operator is formally low rank, with the rank to actually be determined. What's interesting is if we now take the results of Hoyos and Jimenez, cited at the bottom here, for the turbulent kinetic energy, and we overlay those results onto this plot, you can see that the turbulence is living, if you like. The turbulence exists at those scales where the resolvent is low rank. So this particular formulation for the equations, and the key here really is to keep the spatio-temporal setting. Often we look at either the spatial or the temporal data. But if you keep the spatio-temporal representation, you find that there is a low rank approximation for the resolvent, and therefore there is a basis that captures pretty well the physical mechanisms that are present in turbulent flow. There are some deviations out here. There are these very long streamwise structures that must be no forcing to excite these. They're very highly amplified otherwise. And this deviation of the black lines from the DNS, from the color, this is the footprint of structures that are seated at a higher location from the wall. So it's hard without waving my hands particularly effectively to indicate what's going on, other than we know the origin of these two deviations. So now, two things. So the first thing to say is that this low rank representation is particularly amenable now to randomized algebra. So the Halko, Martinson, and Trop paper down here, we can use that technique to approximate the SVD very cheaply. This whole technique, everything I've shown you thus far, in fact, everything I'll show you during this presentation, is so ridiculously cheap, it's all run on my laptop in MATLAB. Now, that's not the most efficient way to do it, but it's so cheap, we don't really care. That's not true if you go to slightly more complex flows, but really this is just based around the SVD. The second thing to say is now that we believe we have a low rank operator, we believe that that is going to capture, the low rank representation is going to capture what's going on in turbulence. We can exploit that, the basis we get from the SVD to write both the velocity field and the forcing field. Now, sigma, psi, and phi we get directly from the analysis of H. These weights, chi bar, and chi, are things that we need either data or analysis to calibrate. So our linear analysis will never give us those complex amplitudes. Now, we want to be able to truncate. Did I just drop out? Okay, I think I'm back. We want to be able to truncate here. Instead of having infinity, we want to reduce this to some rank n representation. And if we do that, we can interact modes. We can interact these psi modes to give us the phi's, and we can write down an expression for the weights, where this coupling term comes from just the resolvent, and the velocity weights, again, are to be determined. Okay, so is this a good basis? That's an important question. So I'm showing here now a channel flow, or at least seem to have lost a bottom plate here, but this is a representation of structure, a measure of called swirl, so connected vorticity in the channel flow. We start here with spatial spectra, so streamwise, spanwise representation of the power spectra of UV, W, those are the three velocity components, and UV. And we have those at various locations, Y sub I. So here are the planes, and we perform a convex optimization to determine what is the best representation of those modes in this resolvent basis, which is now in the two wave numbers and the frequency domain, or in C here. And so this is an example result, and the markers here are proportional. The size is proportional to the magnitude of the weight on a particular mode. We're only showing ones that are larger than 1% of the maximum. So you can see there's a clustering up here. So that is the weights that apply to the mode. So remember, we can get those modes once we have just the mean velocity profile. Now, how well do we do in terms of capturing the flow? So the solid lines here are the DNS results. The filled isocontours are the equivalent level results reconstituted from our resolvent mode. So I'm just showing you the UU and UV results here. Distance from the wall on the x-axis and streamwise wavelength on the wall normal axis. So what's important here is that this representation has been subsampled in the wall normal direction. We use only 60 planes. We've subsampled in the wave number and in the frequency domain. And so we capture more than 95% of the turbulent kinetic energy. The difference is in these little wobbles that you see here, with a fraction of a % of the degrees of freedom of the DNS. So this is a sparse representation of what's going on. But it is a projection, or it's an optimized projection onto the resolvent basis. So the question is, do we get more than we optimized for? And so recall that we optimized for these spatial spectra. We can now look at the spatio-temporal spectra, so the omega kx spectra. And so we do pretty well there, even within this subsampled space. And in this red box now is something that we didn't optimize for at all, and that is the spectrum of the forcing terms of the quadratic term, the Reynolds stress term. And you can see that, again, even though we are significantly subsampled, we do pretty well. So we get more than we bargained for, or at least we set out to do. We get not a self-sustaining or a Galerkin type representation, but even just projecting onto these modes gives us a good representation of the velocity field. I'd like to tell you now a little bit about some of the sort of nitty-gritty details associated with the resolvent. If we look at this formulation, this little schematic that we've seen before, recall that the mean velocity profile is what's governing what's going on in the linear world. On the right-hand side here, I'm showing you that mean profile, distance from the wall, or log of distance from the wall, and here's the mean. And there are 3 Reynolds numbers here. So in this particular scaling, those profiles collapse very close to the wall. There's a logarithmic region right here, circled, and then a wake region shown by these slight deviations in blue, red, and green. And so this logarithmic region, it's often called the overlap region or the inertial region, has some special significance in terms of turbulence cascade of energy, or how energy is moved from where it's produced, predominantly close to the wall, to sustain what's going on further from the wall. But there are some interesting properties that are impressed on the resolvent because of the self-similarity of the mean profile. So let's consider when this might be self-similar. And we can see for this log region that the linear terms, the linear operator, will be self-similar on hierarchies that are governed by these parameters on the right. So YC here is the location of the critical layer, and so that is where the local mean velocity is equal to the downstream convection velocity of the perturbation of the fluctuation. So omega on K is equal to the local mean velocity. So that's not a new result in terms of the stability of flows, but the importance of critical layers, or at least a continuum of critical layers, had not really been appreciated in turbulent flow until quite recently. So if you scale your distance from the wall by the critical layer of the disturbance, the height of the critical layer of the disturbance you're considering, or the bold K you're considering, and you scale your streamwise wave number with essentially distance from the wall squared, and your spanwise wave number by distance from the wall, the response of the resolvent will be self-similar. So the mode shapes are the same. You can scale the magnitudes, and basically the response mode is identical. Now that has some implications for these weights on the modes as well. So the weights on the nonlinear terms. First of all, interactions between hierarchies at any height y are self-similar as you move away from the wall at a different y. And then the weights themselves are also self-similar. I won't have time to go into that to too much detail. So all I'm trying to get at here is that this whole system in this region, if it's isolated with a logarithmic profile, the whole nonlinear piece is self-similar. So let me show you some of that structure. So on one of these self-similar hierarchies, I'm going to look for a geometric scaling here. So I'm going to look at 5 heights, which are governed by yi plus 1 being 2, a of 2 times yi. So these black dashed lines show those critical layers for each of those modes. And I'm showing here the streamwise fluctuation for one particular hierarchy. These are just the parameters in terms of the Reynolds number that we're looking at. Now, if I take this box here and I scale it according to those hierarchical parameters I showed you before, we have something that has a fractal-like behavior. It must have. These are geometrically self-similar. But what's interesting, I think, is that when we look at our experimental observations, our eyes are less drawn to really what's happening, or at least there are many, many modes active, so we wouldn't see such a clean picture here, but we would be drawn to this kind of connected blue feature. And you can see here that a connected blue feature would constitute several members of a hierarchy. And so there's another piece of work, actually it's not, I cited it I think on the next slide, where we go into the connection between this type of representation and a very classical representation called the attached eddy hypothesis, which is based on the superposition of self-similar structures like this. If we look in 3 dimensions, we have these really interesting structures. So this is for a particular level of isosurface, but these are very interesting coherent structures associated with single mode resolvent representation. So just a rank 1 approximation here. The benefit of the resolvent approach is that because we now also have the frequency domain, we're able to look at the relative convection of these modes within the mean relative to the mean. So I'm not sure whether you can see on the top here these things move apart very slowly. So if you look at maybe the edge of one of these shapes, you can start to see that these top modes are moving ever so slightly faster than the smaller ones going down the hierarchy. This lower panel is just showing the addition when you have the mean in place as well. And if we go back to the weights, we can find out that there actually is a scaling with y of the weights on these hierarchy. So we have some nonlinear information. I'm coming up on my time, not too long, so I'm going to speed up just a little bit. This is perhaps the most interesting or most recent piece. What about the nonlinear forcing? So I've told you about a modal representation, so analyzing the linear operator and seeing some things that look promising with regards to the nonlinear term. There's no guarantee. In fact, it would be surprising if this particular analysis of the linear operator was optimal for the nonlinear term. Let's go back to some data right now. We've for some time in the community been interested in the correlation between large scale positive red and negative blue streamwise fluctuation and the streamwise stress, or the square of the small scale activity. Those are not quite equivalent, but on this lower panel here, the black and the white shows the u squared, the instantaneous value of the instantaneous value of the square of the velocity once it's been subjected to a small scale filter, low pass filter. And you can see that it bulges up, and it bulges up when the background, or the large scale shown on the back there, is blue or is slow. And so Marusik, Mathis, and Hutchins have this very nice schematic that says, okay, if I take an instantaneous signal and I decompose it into the large scale, and that's here, and the small scales shown on the bottom, and I correlate those two, I get this correlation coefficient. So here, these symbols are the results from an experiment. So it goes through 0, somewhere that we now identify as being the critical layer of the most energetic large scales in the flow. So the question is, can we do anything about that with this kind of transfer function approach? So far I've been talking to the left side of this screen. On the right side, we are now going to try to look at a transfer function between this UI-UJ term and our original UK. So I'm just going to change notation here to fit the experiments. I'm going to skip this because I'm running out of time. But we have a semi-analytical approach, WKB type. Well, you end up with an airy function representation that holds for the turbulent case too. That tells us that our large scale, our U tilde, has a Gaussian shape. If the U tilde has a Gaussian shape, then our stresses have a Gaussian, just with a higher tilt. And the question is, can we predict the relative phase? And the answer is that if instead of doing the SVD and working through that, we just look at the phase given between these two structures, we do end up with the right phase relationship. So as you cross the critical layer, you should be going from in phase to out of phase. And so this solid line here is what we get from our very simplified transfer function relationship. So around here, we match very well. On the right, we're showing that we have the right sense of phase, and that sense of phase is that, as I said, the stresses are in phase close to the wall and out of phase far from the wall, which is consistent with this image that I showed you from some DNS. Right, I'm going to wrap up and hopefully leave some time for questions. I see there's one in the window already. I've shown you now a story really about the pseudo-spectral interpretation of the forced Navier-Stokes equations, where the forcing is associated with the quadratic nonlinearity. I've shown you hopefully that this shows promise both for the a linear basis or basis from the linear operator to represent a turbulent flow, and that there's this modal puzzle of how you piece things together and what other information you can get from the equations to close this loop on the right. We think of this in flows and then reconstructing the flows. The important piece here again is that the approach that I'm showing you here is very, very cheap. So for a one-dimensional mean channel flow, this is trivially cheap. And there's some hope for efficiency even for complicated flows. So the next frontiers are self-sustaining model solutions and design of control. So with that, I'll end. I'm concluding my talk, but I believe we switch over to a brief question and answer session. Without a moderator, I'm just going to dive in. So I see the Q&A. How does the resolvent decomposition relate to approaches like dynamic mode decomposition? So that's a good question. Everything I've shown you here, remember, was derived from the equations of motion. So it's like an equation-driven version, whereas the DMD or Koopman analysis would be data-driven. And so really the fusion of those two things is how you get the weight to close the loop here. And so one of the things that we're looking at is exactly how you go about fusing those. There's a nice paper by Town et al., also out of Caltech, that shows formally what the connections are between Koopman and DMD and spectral POD and POD and resolvent analysis. We also have a paper showing that the Koopman modes are very much related to the resolvent modes in this traveling wave formulation. I don't know whether there are any other questions. Oh, I see one more. Thank you. You needed a mean flow as an input in your calculations. Where did you, or how did you get it? Absolutely. Yeah. So I mentioned at the beginning that it is an input. So you know, this is typically easier to get in an experimental situation or via a RANS calculation. I didn't have time to talk about it here, but the mean is a constraint actually on this modal puzzle, right? So if you get this right, you get back the mean you started with. What I would have spoken about if I had more time is how you get from laminar to a turbulent mean. So obviously you would like to be able to start from a solution of Navier-Stokes and equilibrium and move forward towards the turbulent mean. So that's something that we can do for exact coherent states, so mildly turbulent flows. It's really non-trivial for these full flows. So that's a limitation, but again, just being able to get something from the equations or to design a mean flow and figure out how to sustain it with an external forcing is something that we're looking into. I see another question. Have you considered any links to the critical phenomena viewpoint recently developed by Goldenfield et al., roughness-induced critical phenomena in a turbulent flow? I'm only vaguely familiar with that work. I will not venture a connection at this point, but I will go and study it. So thank you for that. Okay, I'm not sure whether we get cut off here because I am a little over 2:45. If you have any other questions, please pop them in. Otherwise, I thank you very much for tuning in and enjoy the rest of the meeting. Oh, change the word recent to 2006. Okay, the Goldenfield. And
we can wait another couple of moments, so that's fine, no problem.
So that's okay, Jen. I just see another couple of questions come in, so maybe I can answer those and you can cut me off when you need to.
Most definitely.
The final question on my screen, nope, there's another one. My equations must be space independent for the equations on slide 4 to hold. So I believe you're referring to the Fourier transform. So you Fourier transform in whichever homogeneous directions you have. So this technique gains in expense. It doesn't become prohibitively expensive, but it gains in expense as you reduce those homogeneous directions. It's been very effectively exploited for things like turbulent jets, where you have an axisymmetry that you can exploit, but no streamwise homogeneity. You can use it for things like cavity flows. So it just depends how much expense you want to incur and how much you can get away with, because one can make a scale separation argument about the scale of variation of the mean relative to the scale that you're looking at. But that's a good point, yes. So I've shown you the simplest implementation here. Thank you. Somebody thanked me, thank you very much. question, what does the resolvent analysis produce in the homogeneous and isotropic case? So that's a really good question. So what's giving this spatial localization, and so what's giving you the sparse representation here, is the mean shear. So everything I've shown you here is really predicated on there being a mean shear that localizes the response. In the homogeneous case, or the isotropic case, homogeneous and isotropic case, you don't have that. It's not clear what you would get because you have no critical layer to localize everything. It's not something that we've studied. We've thought about it a little bit. So I'm not really able to give you the exact answer of what it gives you. I'll flip that around to say, if you have a mean shear, then you have a reduction in complexity, which is kind of counterintuitive, I guess. Normally we think of the inhomogeneity associated with the mean shear as causing complications. Okay, I meant the mean flow on equation 4, on slide 4. So slide 4 was, no, those equations are general. As I set up on slide 4, the mean was a function of x, y, and z. The development I showed you for the channel, u is just a function of y. Next question, can the CFD community utilize the findings to make models more efficient instead of utilizing a brute force approach? Well, that's the ultimate goal. So what I'm trying not to do is to reinvent the wheel or reinvent the modeling approach. So a lot of our effort right now is trying to find out from the modelers what is useful in terms of what can we distill from a resolvent analysis up front versus what can we embed in a modeling approach. So for example, in LES, there's a lot of potential for warm models, I think, to be developed out of this resolvent analysis. You know, in an ideal world, one could say if you have a self-similar profile developing, you only solve this modal puzzle once, and then you know how to extend this for other Reynolds numbers. So yes, that's certainly something we're looking into. Question, did I see any numerical difficulties in the simulation? Finite different systems of bad condition numbers so that iterative solvers fail to converge. Is that, with regards to the SVD, no. So when, as I mentioned, especially when that operator, the resolvent, is low rank, you can use various ways to get at least the first singular mode. So that's, there's no difficulty in that. If you want to go a long way down the SVD, then yes, you might have trouble. I'm not quite sure what finite different piece you're talking about. Not quite sure how to answer that without being able to get maybe you can tell me which specific piece you're concerned about having a bad condition number. Sorry. What papers would you recommend for further reading? So I think there's a lot of work related to just analysis of the resolvent in the general literature. The things I'm going to recommend are related to fluid mechanics, engineering, and turbulence. So the Jovanovic and Bamier paper from 2005, it's in the Journal of Fluid Mechanics, really set up what we call the input-output method for thinking about thinking about flows. And so that's really foundational if you want to think about things like masking input and output to see which components on the input drive which components on the output. So I think that's an important piece. The early work on transient growth sets the scene. I would say that the 2010 paper, McKeown and Sharma, was where we realized the importance of critical layers for wall turbulence. If you want to think about modal decompositions broadly in fluid mechanics, there's a nice AIAA journal review paper. It was led by Sam Tyrer from UCLA. I'm a co-author on that along with maybe 20 other people, but that goes through things like DMD, POD, so data-driven techniques, and then equation-driven techniques like the resolvent. If you're really a sucker for punishment, I wrote an 80-odd page perspectives paper for the Journal of Fluid Mechanics related to the application to wall turbulence. That was 2017, so we've come some way since then. You can find some of those on my website, just mckeown.caltech.edu, but there's quite a broad literature right now, so it depends how deep you want to go. Happy to respond via email. And thanks, enjoying the use of MATLAB graphics. Well, thank you very much, Caltech alum Cleve Muller. Jen, are we still okay?
Yeah, you are. We're going to need to release this in about 4 minutes.
4 minutes. Okay, I see 2 more questions, so let me answer those and then call it quits. What can you tell about the boundary conditions? Well, what I showed you is for a channel. So here everything is very clean. In terms of the data, and then in terms of if you do this when you have a spatially developing flow, you have to pay attention to that. I don't think that there's a silver bullet to tell you how to do that. It's the same problem that you have if you're trying to do global stability analyses. So there's certainly some work to be done there. There's sort of a fine art when you move away from the simple representation that I showed you here. And then the last question, maybe more as a classroom question, is there a mathematically intuitive explanation about the generation of the self-similar structure? So yeah, this is sort of intriguing on several levels. The way we came to this, I think, and a lot of this goes back to Alan Townsend in the 50s, 60s, and 70s. If you think about a length scale argument, you find out that close to the wall, viscosity is going to be important. Far from the wall, viscosity can't be important, and sort of outer length scales or boundary layer type length scales are important. And if you work backwards from that, you find out that there's a region in the middle of the flow where the only important scale can be distance from the wall. So that's y. And so that's reflected in this logarithmic mean profile. And, you know, as we know mathematically, logarithms have a lot of special properties. So self-similar structure is really associated with the important scale being the distance from the wall in some region of the flow. So I don't know whether that's intuitive or not, but that's certainly the length of answer that I have time for right now. So again, I'd just like to thank you all very much, first of all, for coming to a virtual meeting. It's my first virtual meeting and first virtual talk. And thank you for all the interesting questions. And thanks, Jen, for overseeing everything. And
my pleasure.
That I'll conclude.